Welcome to lecture 3 of module 4. Till last couple of lectures, what we have discussed is that how to get different dimensionless groups to define a system, and we have shown two cases, for a forced convection case and for free convection case. We have shown and we have found out different dimensionless groups. Now, we will carry forward our discussions to see that using those dimensionless groups, what are the various types of empirical relations, correlations that do exist, that being suggested and reported by various researchers, and which are being used in practice to calculate the values of heat transfer coefficient or convective heat transfer coefficient, at the same time to calculate the values of total rate of heat transfer through a particular system. So, now as we have discussed in the last lecture also that there are various possibilities for the systems, like it can be internal flows, it can be external flows, okay, it can be flow through packed beds. So, we will be distributing like this way, and now today we will be first discussing the internal flows. That means, so correlations, various correlations which are available for internal flow. Internal flow means flow of a fluid through a device, and heat transfer is accompanied with that. So, that kind of situations we are going to discuss, but before we discuss these various correlations that is there, we will discuss a few terminologies. Which are very important for understanding these correlations, which is very important to understand the heat transfer phenomena. First of all, is the characteristic length. In many a times we have seen the characteristic length is used. Now, what is this characteristic length? It is defined based on the geometry of the system. So, characteristic length is defined based on geometry of the system. Now, if we take an example, say, so flow through a pipe for flow through or heat and mass transfer in a pipe, the pipe diameter is taken as characteristic length. Okay. Now, similarly, when we have flat plate, for flat plate is the length of plate from the leading edge. Similarly, flow through for packed bed it may be the particle diameter is used as characteristic length. So, this way we can have different characteristic lengths for different situations. Okay. Now, next terminology what I am going to discuss is that bulk temperature or mixing cup temperature. So, if I say it to be say T b, we can assume, we can understand that it is the average temperature, fluid temperature in a cross section. So, if we consider like a tube is there, this is the center line and this is the cross section. So, in this cross section, the bulk temperature and mixing cup temperature is the average temperature in this cross section. In a cross section, is T b. Okay. So, we can have in a pipeline, we can have that bulk temperature calculated like this way, say T b will be equal to, for a pipe flow, say 0 to r, r is the radius of the pipe, 0 to r is the 2 pi r into dr into V z, this is the z direction, okay, V z, this is the 2 pi r dr is the differential area into V z is the flow rate, volumetric flow rate, this becomes volumetric flow rate and then multiplied by rho, that becomes the density of the fluid that is flowing through this cross section, and C p is the heat capacity of the material and T is the temperature at that position. So, if I consider any cross sectional region, and in that region say 2 pi r into dr, if we take a smaller element of this 2 pi r into dr, 2 pi r into dr into V z, V z is the velocity at that particular point. So, 2 pi r dr into V z is becoming the volumetric flow rate into the rho, that means, it is become the mass flow rate into C p, that means, heat capacity flow rate into the time temperature, that is becoming the total energy flow, that is the total energy flow is becoming m C p del T, T minus T reference is taken as 0 divided by heat capacity, that is again 2 pi r dr V z into again rho and C p. So, this is the expression that gives us the value of bulk temperature or mixing cup temperature. So, it is like this, mixing cup temperature means in a cup there is a fluid and we are whole fluid is mixed up. So, the temperature of the fluid within the cup becomes like uniform and it is everywhere in the cup it is the same. That means, here everywhere in this cross section the temperature is to be T b, which is constant, which is fixed, that is called mixing cup temperature or bulk temperature. Okay. It is basically the average temperature in a cross section. That is very important things that we should know. And then many of the correlations are being based on average bulk temperature. So, it is nothing but if we have a pipe and say here it is say this is the input and here it is say T b I and here it is T b O, this is output, in out. So, that means, T b I is the bulk temperature at the input, T b O is the bulk temperature of the output. Therefore, then average bulk temperature if is this T b average is usually the arithmetic average and that is equal to T b I plus T b O by 2. That is also one important information that we should know. Then another thing is that wall temperature, that is also very important. So, wall temperature we usually will be denoting as T w. Wall temperature is the temperature of the wall, that is from the name itself we can understand. Now, many situations we may find that correlations are used for constant wall temperature, sometimes it is used for constant wall flux. When there is a constant wall temperature, then it is becoming T w is constant all throughout the surface, and all throughout the wall, whereas when there is a constant wall flux, then T w may not be constant, T w can be a variable quantity. Okay. So, this is called wall temperature, and then we have another temperature that is called film temperature. In the film temperature, we have I will be usually denoting as Tf. Tf is given as Tw, that is the wall temperature, plus Tb, the bulk temperature at any location. I am sorry, it will be T infinity, that free stream temperature. I will come to that, what is free stream temperature, by 2. So, T infinity is called free stream temperature. So, there is another temperature that comes into picture, is that free stream temperature, and that is T infinity. So, film temperature is the arithmetic average of wall temperature and free stream temperature. Now, this free stream temperature, from the name itself we should understand that the stream of fluid is free from some kind of interaction. That means, it is the free from the effect of the wall. That is why it is called a free stream temperature. Okay. When we will be discussing the boundary layer theories, there we will be discussing little more details about these free stream conditions. Okay. And then there is another one that is called logarithmic log mean temperature difference. Usually it is called to be LMTD. Sometimes we will refer to it like this delta 2 LM, that means long mean temperature difference. It is like this for two streams that is flowing, say this is in co-current direction, co-current flow. Co-current means that both the streams, is stream 1 and this is stream 2, they are flowing in the same direction. So, this is the temperature difference for this 2 is delta T 1 in this side station 1, and this is station 2, that this is say temperature difference between these two streams, this is say delta T 2. So, this is the temperature difference in the left station station 1, and that is the temperature difference delta T 2 in the right station, that is station 2. Then delta T L M is the log mean temperature difference, and that is becoming equal to delta T 1 minus delta T 2 by delta L N ln delta T 1 by delta T 2. So, this is becoming the log mean temperature difference. This is also very frequently being used in many situations. So, we will be discussing even details about this log mean temperature difference when we will be discussing about that performance of the heat exchangers and all this. Okay. Now, we have got some ideas about that various terminologies. Okay. Now, what we are going to do is that we are going to see the various correlations, those are being used particularly for different kind of flow situations. To start with, as I have started with, that we will be discussing first the internal flow situation. Internal flow means we will be discussing the flow through a device. Now, this device can be a circular duct, it may not be a circular duct. So, this device can be a circular duct, slash you can say to a pipe or tube, and another it can be non-circular duct. And also this flow through a device can be your laminar flow and it can be turbulent flow. Usually what is being done, that flow, when there is a flow through a device, it is expressed, its flow characteristics is being decided by the dimensionless group. Already we have discussed in some places that it is decided by a dimensionless group, that is called Reynolds number. And we will say that in case of flow through a pipe, flow of diameter d, we will say that it will denote like this: RED is equal to d v bar rho by mu. What is this? Now, d is the diameter of the pipe, naturally it is the inner diameter of the pipe. V bar is the average velocity through which it is flowing, average velocity by which the fluid is flowing. Rho is the density of the fluid and mu is the viscosity of the fluid. So, d is pipe diameter, then v bar is velocity, average velocity of fluid, and rho and mu are density and viscosity of a fluid. Okay. So, when we have flow through a non-circular duct, so when we have a flow through a non-circular duct, then it will be little bit changed. So, when there is a flow through a non-circular, we will have Reynolds will be written as REDE, and that will be DE rho V bar rho by mu. Now, this DE is called equivalent diameter, equivalent diameter, and it is written as 4 into RH. This is RH is called hydraulic radius. And this is equal to, this is defined as flow area by weighted perimeter. Okay. This is defined by flow area by weighted perimeter. Now, let us consider a channel flow through a rectangular channel of sides A and B. Okay. Then what will happen? RH is equal to flow area will be A into B by weighted perimeter will be 2 into A plus B. Then DE will be equal to, equivalent diameter will be equal to 4 AB by 2 into A plus B, and that is equal to 2 AB by A plus B. Now, there are certain situations that this equivalent diameter can be different when there is a fluid flow situation, can be different when there is a heat transfer situation. So, for fluid flow and heat transfer situation, equivalent diameter may not be the same. Typical examples I will tell. For example, a flow through annulus. If we consider this, so we have this, says that this is the outer pipe and this is the say inner pipe. Okay. Now, this is the diameter of the say inner pipe, and this is the diameter of the say outer pipe. So, this diameter is the outer diameter. So, di, if we say that di is outer diameter of inner pipe and DO equals to inner diameter of outer pipe. Now, what we see in this case, when the fluid flow in the annulus, that means the fluid is flowing like this in the annulus region, a fluid is flowing. In that case, the fluid is flow area is we can understand that pi by 4 into dO square minus di square. Okay. Outer this is the flow area of the pipe, flow area of the fluid through the annulus region. Okay. Now, weighted perimeter, because the fluid is flowing through the annulus region, it is weighting in both the sides. So, weighted perimeter is pi into dO plus di, because both the tube surfaces, the outer surface of the inner pipe as well as inner surface of the outer pipe, both are getting weighted by the fluid flowing. So, therefore, the equivalent diameter becomes, so for this case that equivalent diameter will be becoming, if we do the calculations, we will get that flow area by weighted perimeter. So, it is actually now dO minus di. So, this equivalent diameter is used, dO minus di is used for calculation of hydrodynamic situation, that means for calculation of pressure drop. So, when we have non-circular ducts, when there is a flow through a non-circular duct, and if we are interested to know about the hydrodynamic situation, if we want to know about the pressure drop, then we may have to use the diameter, and that diameter which is used is called the equivalent diameter, and here it will be d naught minus di. But when we consider about the heat transfer situation, then that case, if we see carefully, the heat transfer is taking place between the inner fluid of the inner tube and the fluid in the annulus. So, basically this is the region where the heat transfer is taking place. So, only one surface is being involved for the heat transfer situation. So, it is not both the surfaces, it is not the outer surface of the inner tube as well as inner surface of the outer tube. So, outer tube surface is no way involved in any such operation. Therefore, we will be having weighted perimeter for these situations will be for heat transfer weighted perimeter is changed, though flow area remains the same, but weighted perimeter is pi di. So, therefore, for heat transfer dE equivalent diameter becomes for heat transfer it becomes 1 by di into dO square minus di square. Okay. So, this is what that we should know, that in case of non-circular duct we can use the equivalent diameter for calculating the heat transfer coefficients and for applying or for calculating the Reynolds number, and then for calculating the heat transfer coefficients by using the Reynolds number expressions in some correlations. Okay. Now, what we will see is that internal flow will first consider the laminar flow. Now, there is a question of laminar flow and turbulent flow. When there is a laminar flow, when there is a turbulent flow, we have some idea from the fluid mechanics, but still just as a reminder we can say that when Reynolds number which is based on the diameter, if Reynolds when the flow is internal flow through a device and Reynolds number is expressed as RED, we have to be very careful about that. Reynolds number expression is RED is based on the diameter of the inner diameter of the pipe or tube through which it is flowing, or equivalent diameter, or REDE. Under this situation, if this is less than 2100, then we call it to be we call the flow to be a laminar flow. Then if RED or REDE, D means based on equivalent diameter, is greater than 4200, we call it to be turbulent flow. And between 2100 and 4200 is the situation when transition from laminar to turbulent flow takes place. So, that is why this situation, which is transition region, in that region the mechanism of flow is further complicated. Anyway, so we will now see that internal flow, laminar flow. So, laminar flow, internal flow, then flow through smooth tubes. Slush pipes. So, when we have flow through smooth tubes or pipes, laminar flow and internal flow, under that situation for fully developed flow, at constant wall temperature, Hausen in 1943 has recommended that NUD, that is Nusselt number based on diameter. Okay. NUD is equal to 3.66 plus 0.0668 into D by L into RED, Reynolds number based on diameter, into Prandtl divided by 1 plus 0.04 D by L into Reynolds based on diameter into Prandtl. Okay. This whole to the power 2 by 3. Now, here already as I told, the Nusselt number is based on diameter and it is H d by k, and this H is basically that average heat transfer coefficient throughout the length of the tube. So, H bar and RED is d v bar rho by mu, and we know that Prandtl is equal to mu Cp by k. All these things are known to us. So, if we say that H bar d is the diameter of the pipe, L is the length of the pipe, okay, and H bar is average heat transfer coefficient over the length of the entire length of the pipe. Okay. So, and rho and mu are the viscosity and density, k is the thermal conductivity, these are usual meanings. V bar Cp is the specific heat and V bar is the average velocity through the pipe. Now, one thing we can see that for very long tube, what we have that nozzle based on diameter is becoming now only 3.66, because the rest of the parts becomes negligible. So, for a very long tube, nozzle based on diameter is more or less a constant quantity, which is equal to 3.66. Now, it is being also a similar thing has been reported by Sailors, Tribus and Klein in 1956. What they have said that for fully developed laminar flow, for uniform wall temperature, that is Tw, in that case nozzle D based on diameter is equal to 4.36, which is a constant quantity. And they also have said that for, I am sorry, this is for the first one is for universal nozzle is this is 3.66, and for uniform wall heat flux at the wall, NUD is equal to 4.36, that is also a constant quantity. So, this relationship has been given by Sailors and Tribus in 1956. So, we can see that for when there is an uniform wall temperature, then nozzle number is 3.66 when that length is very high, but Hausen has given some extended form of that. So, it has generalized this, and when L is very high, then it is becoming 3.66. Now, a few things we can see here that this in the previous expression of Hausen, we have seen that there is a terminology that RED into Prandtl. So, these things also can be written in many places. It may be seen as the Peclet based on diameter, and this Peclet based on diameter, this is called Peclet number. So, what we get is for Peclet number is Peclet number expression, we can say it is, or if we say that it is based on diameter, we can say that it is like this d V bar rho by mu into mu Cp by k. So, this gives us d V bar rho Cp by k. So, if we rewrite by some rearrangements, then it becomes rho V bar Cp delta T by k delta T by d. Now, if we see the top and bottom portions, numerator and denominator, we see that numerator is nothing but heat removal by bulk flow, and denominator is heat removal by conductive flow. So, we can say that heat transport, we can say it like, or we can say that this is also can be written as V bar into delta T by alpha delta T by d. Okay. So, this is nothing but like a Fourier law. So, heat transport by thermal diffusion, it is by conduction. Okay. So, we will say that it can be written as heat transfer by bulk flow due to the velocity and heat transfer by thermal diffusion, or you can say that conductivity or heat transfer by conduction, whatever you say. So, it can be said like that. Thus, we can say that similar kind of things can be there even in case of mass transfer. So, therefore, we will be to designate whether it is a Peclet number for heat transfer or Peclet number for mass transfer. We can have two Peclet numbers actually, one for heat transfer, one for mass transfer. So, we will write it to be that P E D, and that is for heat transfer. Similarly, we can have Peclet number based on diameter for mass transfer. This is for mass transfer. That also is possible. Okay. So, there are two terminologies, one is Peclet number, and that is for heat transfer, that is for mass transfer. In the present situation, in the for these particular discussions, we will be concentrating on the Peclet number for heat transfer, P D, and D indicates that is based on the diameter of the diameter of the or the characteristic length of the flow device through which the fluid is flowing. Okay. Also, we can see that if we just see the product P Peclet into D by L, this is also called Grage number. Grage number. This is defined as Grage number, ZZ, Grage number. Okay. So, this Grage number is nothing but it is just some modification of the Peclet number, where D by L, that aspect ratio is being taken care of to take care of the entrance effect. So, D by L, this is multiplied to take care of the entrance effect. So, this is called Grage number. Now, we have seen that one typical expression for laminar flow situation, and we have seen that how the equation comes, that correlation, that is the Hausen correlation. Now, there is a better or simpler correlation, I should say, not better, a simpler correlation which is very frequently used, is given by Cedar and Tate. In 1936, it is also called as Cedar-Tate equation. It is like this: Nusselt based on diameter is equal to 1.86 into RED into Prandtl to the power 1/3 into D by L to the power 1/3 into mu by mu W to the power 0.14. Now, what we can see, this also we can write as that 1.86, and already we have seen Reynolds into Prandtl is Peclet and into D by L is called Grage number. So, we can write it to be ZZ to the power 1/3 into mu by mu W to the power 0.14. So, this mu and mu W both are viscosities of the fluid at different temperatures. Okay. Now, what are the restrictions for these cases? This relationship is applicable. It is applicable when as I said, that Grage number is greater than 10, and all the fluid properties are evaluated at the mean bulk temperature of the fluid, as I told previously that it is a TB bar, okay, except mu W, which is evaluated at T equals to T W. wall temperature. So, mu w is the viscosity of the fluid which is evaluated at wall temperature. Okay. Now, in addition to whatever I have discussed, a little thing is supposed to be discussed, which is called, there is another terminology that is called Stanton number, which is very frequently used in many situations of heat transfer characteristics. So, Stanton number, it is actually is defined as Nusselt by Reynolds into Prandtl. Now, if we see that Stanton number, that expression, if you just put all the values of Nusselt, Reynolds and Prandtl, we will see that it is H say L by K, in this case it is D, H D by K into D V bar rho by mu into mu C p by K. So, it is becoming H into V bar into rho into C p. So, then we can again write that Stanton, if we rewrite again, H into delta T by V bar rho C p into delta T. We can understand that the first one is, if we again multiply by the area A H, or rather H A delta T by rho into V bar into A, this is the volumetric flow rate, into rho the mass flow rate into C p into delta T. So, heat transfer due to bulk flow. So, we can say that convective heat transfer by heat transfer by bulk flow. So, we can see the differences between these. Now, here it is the Stanton number, and previously we have discussed about the Peclet number. In case of Peclet number, we have seen that it is heat transfer by bulk flow, by heat transfer by thermal diffusion or conductive heat transfer. But Stanton number says it is convective heat transfer divided by heat transfer by bulk flow. So, we have some relationship between that bulk flow heat transfer to convective heat transfer or conductive heat transfer, either by Peclet number or by Stanton numbers. So, Stanton number is very commonly being seen, and similar to Peclet number, Stanton number also can be for mass, can be for heat, because as we shown here that it is convective heat transfer and the heat transfer by bulk flow. Similarly, we can have convective mass transfer and mass transfer by bulk flow. So, therefore, we will write here Stanton number can be Stanton heat or Stanton mass. In the present case, it is Stanton heat, that is Stanton number for heat transfer. Okay. Now, in addition to whatever I have discussed, there are some correlations, particularly in case of liquid metals. As we know that flow of the liquid metals would be a laminar region, where here it is Prandtl number is low Prandtl number. Under that situation, Nusselt based on diameter is approximated as 8.0. It is a constant value for uniform heat flux, and Nusselt based on diameter is equal to 5.75 for uniform wall temperature. Okay. Now, in addition to this, whatever when we have started with a case of flow through smooth tube. Now, when the tube is rough. So, when the tube is rough, that means the tube surface is rough. When tube surface is rough, there is all these correlations whatever I have told regarding the flow through a tube or pipe and laminar flow, these correlations are not very useful. The correlations are not very useful, and many a times we have to depend on these are not very useful because they may not give predictive results. So, many a times we have to depend on some analogical equations between fluid flow or fluid friction and heat transfer. What I was trying to emphasize over here is that as the surface roughness increases, the friction of the fluid with the surface increases, and there can be a huge amount of pressure drop because of this friction. There can be huge amount of change in the velocity profile, there can be a change in the pattern of the flow, and as a result the mechanism of heat transport also is going to change. The convective heat transfer coefficient, which is a flow property, it depends upon the flow rate and all. So, types of mechanism of flow, so many things it depends upon, as we have seen. So, therefore, the H value prediction of the H value may not be an accurate prediction, and we may land up with some false estimations. Okay. Now, what we will do is we will take up a problem that will discuss to some extent on the demonstration of the various dimensionless equations that we have discussed. So, the problem is, say first problem is, say it is desired to heat water, it is desired to heat water through a flowing through a tube, flowing through a tube. Okay. Water enters at 50 degree centigrade in the tube of diameter 2 centimeter and length 3 meter. Okay. The average velocity of water is through the tube is 2 centimeter per second. Okay. And the wall temperature of the tube is maintained at constant temperature equal to say 80 degree centigrade. Okay. Now, what we have to do? Calculate the exit water temperature. Okay. Now, given at 50 degree centigrade, mu is equal to 5.0 into 10 to the power minus 4 kg per meter per second, then rho is equal to 990 kg per meter cube, then Cp is equal to 4.18 kilojoule per kg per Kelvin, and then thermal conductivity K is equal to 0.65 watt per meter per Kelvin, and mu W is equal to, that means at 80 degree centigrade, 3.5 into 10 to the power minus 4 kg per meter per second. So, we can see that for this problem we have to calculate the exit water temperature. A fluid is flowing through a tube and its surface is a constant wall temperature condition. Now, what we will do is, if we see that Prandtl number is equal to mu Cp by K, and that is equal to 5 into 10 to the power. Now, if we are working on the solution part of this, is 5 into 10 to the power 4 in minus 4 into then 4.184, and we have to be 4.180. We have to be very careful about the units. It is given as kilojoule. So, we have to make it to multiply by 1000 by 0.65. So, this becoming, so Prandtl number is becoming 3.22, and let us check the Reynolds number and try to understand whether it is lying in the Reynolds laminar region or it is lying in the turbulent region. That is what is very important to know. So, accordingly we have to use a particular correlation. So, we will write now d v bar rho by mu, and one thing, we are calculating this Prandtl number and Reynolds number on based on inlet temperature property. So, at all the calculations we are doing at inlet conditions, because we are given the values at inlet conditions. So, Reynolds number is becoming 0.02 into 0.02 into 990 dV rho by mu 5 into 10 to the power minus 4, and this is become equal to 792, and which is well below 2100. So, we can say it is a laminar flow. So, when it is becoming a laminar flow, we will see that we will try to use Siddharth equation. But when we have to use Siddharth equation, we have to check that whether Grace number is greater than 10 or not, that to be checked. So, Grace number is, we know that it is Reynolds into Prandtl into d by L, and if we see, if we put the values, is 7.792 into 3.22 into d 0.02 by 3. So, it is becoming 17, which is greater than 10. So, Siddharth equation is applicable. So, it is applicable. Okay. Now, once it is applicable, now let us try to find out what is Nusselt number. Nusselt number is 1.86 into Reynolds diameter. I am sorry, why should I write all this? So, we know already it is Grace to the power 1/3 into mu by mu w to the power 0.14, and if you put the values here 1.86 into 17 to the power 1/3 into mu by mu w is equal to that already we know, it is given 3.5 by 5.0. I am sorry, it is just reverse of that. It is 5.0 by 3.55 whole to the power 0.14. So, this is approximately equal to 4.5, okay, 4.5, and then or 4.55 approximately equal to this, and then from there we can find out what is H bar or average heat transfer coefficient. This comes about, it is 4.55 into d by k, and this is becoming now 147.9. So, we have got a value of heat transfer coefficient. Now, we have to find out that actually that temperature. So, if we find out the temperature, that should be found out temperature, we should find out from energy balance. That means, the heat transferred is taken that is the sensibly taken away by the fluid. So, we can get is like this, that H bar pi d L into T w minus T b 2 plus T b I plus T b O, 2 bulk temperatures by 2. So, this is H a delta T, H a into delta T, that will be equal to m dot C p into T b O minus T b I. So, this is that sensible heat that is being taken away by the fluid. M dot is the mass flow rate of the fluid. So, if we put these values here, we will get that 147.9 into pi into 0.02 into L is 3 meter into 80 minus 50 plus TBO. TBO is of importance to us, it is not known. We would like to find out that is equal to this m dot is can be calculated that as 6.22 into 10 to the power minus 3 into TBO minus 50, and we are writing all in Kelvin because we are finding that differences in the temperature. So, therefore, Kelvin and centigrade does not matter. So, we are writing all the temperatures in terms of centigrades, okay, into C p is equal to 4180. So, and this m dot is the mass transfer or mass flow rate that can be calculated as pi d square by 4 into V bar into rho. So, m dot is rho V bar into pi d square by 4, and that value is 6.22 into 10 to the power minus 3 kg per second. So, then from this we can find out that TBO from this relations, previous relations, we can find out TBO as 60.5 degree centigrade. Now, this TBO is the exit temperature of the fluid which is being required, but what we have done is all the calculations we have done using the temperature of the inlet, using the properties at inlet conditions. So, we have to now upgrade the properties based on the actual exit conditions, because we have to grade the properties at mean bulk temperature. So, mean bulk temperature now TB mean or TB average is becoming now TBI plus TBO by, I am sorry, this value will be 70.83 or nearly equal to 71 degree centigrade. So, this will be becoming now TBI plus TBO by 2, and this is 60.5 degree centigrade. So, we have to now redo all calculations, all the previous calculations whatever we have done, we have to redo all the calculations and see till or rather it is called trial and error. We have to do this trial and error methods. We have to continue this method till that old TBO and new TBO matches. So, we have to find, we have found out TB bar, then repeat all calculations to get new TBO. Okay. So, like that we will be getting a new TBO. So, repeat all calculations means we have to calculate what is this repeat of all calculations means we have to get all the fluid properties at TB bar gate, and then repeat the calculations and then get new TBO and continue the search or continue the work till the old TBO and new TBO matches. Then that is called the external temperature of the fluid, and H, the corresponding H H bar is the heat transfer average coefficient. So, basically this is becoming repetitive, and through these repetitions we will be marginally improving the values that we are calculating. Okay. So, this is a demonstration of the problem that of the flow through internal tube in laminar flow situation, and flow through a pipe in under laminar flow situations. Now, in the next class we will see the flow through a pipe or flow through any devices under turbulent flow situation, what are the correlations are available, and we will take up some problem and try to demonstrate how this problem is to be solved. Okay. Thank you very much.